Hello and welcome to our presentation. After we just have seen our beautiful introduction video, I would just say, let's go into the presentation. So basically, what is it what we just saw in the video? So our project is basically concluding out of a NEMA 23 stepper motor, which is maximum giving 3 Newton meter of torque and approximately until 1000 RPMs. Also, in addition to that motor, we have a motor driver, which is working in closed loop control, and it also is able to give fault detection. And in add-on, we also have an optical encoder, but the encoder is inside the motor. So just in case if you're wondering later why you don't see an encoder, it's just the black cable. From that encoder, we can get the speed and the position mainly. Also, furthermore, we have the temperature sensor, and it gives us the values of the temperature analog, not digital. And also in addition, we have yes, okay, thank you. We also have the MPU 6050, which is a gyro acceleration meter. It detects the vibrations and the eventual, maybe it happens in the future, maybe mechanical dysfunctions. Also, we have a current sensor up to 50 ampere, and it's measuring the current draw we have as a load estimation. And last but not least, we have a piece of mass we just put on the motor shaft on the top to get a better simulation of the load we have, because in the industrial sectors, every stepper motor which is used has a mass on it. It's just the normal way, and just to make it more realistic. So basically, just for revision, what is a stepper motor? A stepper motor is an obviously electric motor, and it is moving in discrete and precise steps, and it is also working on electrical pulses, and these pulses are resulting in a defined angular movement, so it makes step, 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 and this is where we accurate. So this is one benefit, and it also has an excellent repeatability. And also it has a quite simple control logic, because you have just the steps and the direction. And because also that it is robust and reliable under many different loads, it is also cost effective and precise on the motion control, because of the many steps. And this makes it as a perfect example, because it is often used in the industrial sector, for example, in CNC machines, and also in 3D printers, for example, but furthermore also in conveyor systems, and furthermore, last but not least, also in robotic arms, for example. And that's the reason why we have come to the conclusion to use a stepper motor as part of our digital twin project, because it is highly relevant in real world applications. So it's quite useful and interesting, we have thought. Our goals basically are to get out of these raw measurements all of these values, for example, like mentioned before, the rotation speed, the RPM, but also the ampere, the degrees, out of the temperature, but also the vibration levels X, Y, Z. Out of that, real inputs from the sensors, we want to create our digital twins, and that's what we have done. We have created out of these twins a health monitoring system, and out of that we can see the load estimation, but also the terminal stress, the vibration status, and also in the future a trend of failure risk eventually, maybe. This is not what we have implemented yet, but it is possible to make a decision out of that real use. So what to be exactly where the steps to go to get these goals? First of all, the to-dos where we needed to make a capturement of the physical system. That means we need to set up the sensors and its behavior. And out of that, we need to transform the raw measurements into structured data. meaning that the twins needed a properly created JSON model. And out of that, we can derive health related metrics from the twins. That's what we want. And out of that, we basically provide then the monitoring and prediction. So to do all of that steps, you can just continue. We set up the whole basis with this electric circuit. Sorry.
Okay, let's have a look at our electric circuit and microcontroller management here. For our project, we use two microcontroller. First, the Raspberry Pi 4 and the Arduino Uno R for Wi-Fi. The reason why we use those both microcontrollers is because we have this load sensor, and it provides us analog data, which is especially for the analog to a digital converter on the Arduino. This data, like at a load we are getting out of the sensor, is being transmitted via serial connection to the Raspberry Pi. Also connected to the Raspberry Pi is the vibration sensor and the temperature sensor. The stepper motor is controlled by the stepper servo driver, which is being powered by our power supply with 24 voltages. Now let's have a deeper look into our C code on the Arduino. We are controlling the stepper motor with the Arduino, and we are doing acceleration and deceleration, which we're calling a ramp up. We are looping this every time, so like the acceleration and deceleration lasts for around 30 seconds and then it repeats. So we can see changes throughout our tests. And also we are serial printing the RPM, the current, and the load, which is being provided from the Arduino. And this serial print is being sent to the Raspberry Pi. So now let's look into the code, which is running on the Raspberry Pi in our Python code. We are establishing an MQTT connection to the MQTT service. And we are receiving the data from the Arduino, as I told you, through the serial connection. The data we are getting is being parsed, and the values like RPM and current and load is extracted from this string, from the serial print string. And each value is put to the payload, and the payload will be put inside of the MQTT message, which is published right here to the MQTT service. The MQTT service is running on the Minikube. And each type of data, like our vibration or temperature, has its own topic on the MQTT service.
Via quick insight about our architecture, we have put up some diagram elements here, and it looks quite familiar because of the one on the OpenTwins documentation. It's quite near to it, but we have lightly adapted it. So here's one walkthrough if one sensor is sending a value or producing it and sending it to the telemetry. So the sensor or device is publishing the telemetry value via MQTT to Mosquito basically. And Ditto consumes this MQTT value and updates the twin state. And also Telegraph ingests then this telemetry and writes the time series into InfluxDB. And from there on, in Grafana, there can be seen some values, because Grafana obviously, like everyone know, reads from InfluxDB, and therefore we can see these dashboards and values in Grafana. Grafana also reads on Ditto and its extended API for the live twin view. Also, last but not least, we have changed this whole setup to an ingress setup. That means we don't need to open up single port forwarding tunnels anymore. We just need to set up one port forwarding for the ingress itself, and then we have made up some individual URLs for the different services here on, for example, Ditto, Grafana, MQTT, or the extended API. So we have made it a little bit easier here for ourselves. So basically, just for your interest, there's a tool called K9S, and with this tool you have an own terminal interface, and with that you can see your whole pods inside of your local Kubernetes cluster, and it makes your life a whole lot easier because you can interact with these pods just in a matter of seconds with a few instructions which are displayed on the top. And I just wanted to mention this tool.
Yeah, so now let's head on with our twins and types and how we arrange them in the OpenTwins plugin, which is implemented in the Grafana. We have two types, one type for motor and one type for sensors. We did this decision because we have several sensors, and we were thinking about every sensor must be from the type sensor. And our motor and our stepper motor driver is from the type motor. So this is why we did this decision. We also put some pictures inside of it and added a description. Okay, let's head on to our Influx database and Grafana dashboard. Here we are inside of the Influx database, and we see the data explorer. We have filtered to MQTT consumer, and right now we're looking at the temperature throughout the last 6 hours. As you can see, the value changed, and the data is being published through MQTT to the database. In Grafana, we have 4 panels. First off, the temperature panel. It has last temperature, minimum temperature, and maximum displayed here. And it's quite the same because we're just looking at a small time range. But if I put this to like the last 24 hours and have a look on this time here, we can see when we started with our project, the motor just had around 25 degrees Celsius and heated up constantly to around 42 degrees Celsius. And yeah, that was the temperature where it was stable at. That was exactly the temperature curve we would expect. Yeah, and we see no spikes here. So in case of predictive maintenance, if there would be any value being out of this range, like if the motor is having 60 degrees Celsius, it would be suspicious to us. Next to the load indicator panel, if I zoom in on here, we can see that the load is increasing. to its peak, and then it's decreasing again. And yeah, this is because the motor is speeding up and is speeding down. So the load is getting more and is getting less. Here we have our panel for the vibration sensor. The vibration sensor gives us the sensor for X, Y, and Z axis. And we can see it's fluctuating a lot. And when we accidentally touch the vibration sensor, there will be a big spike here. Yes. So we have filtered this out. So we can only see our relevant data here. And in the past time, we have seen that when the motor accelerates, also the vibration is getting more. Next on to the motor panel, we have displayed this in this way, and we can see the actual RPM being here displayed. Yeah, let me change this right now. Yeah. Let's go back to our presentation. Throughout the project, we had some challenges and difficulties. For example, the sensor reliability and signal interpretation. We had one big spike at the vibration sensor when we touched it, and yeah, it kind of messed up the whole graph here, because we couldn't have a closer look at the normal vibrations because it automatically scaled up. But the problem was solved by adding a filter to the query in Grafana. So we only look at the values in this range, not those spikes. Another thing was that the RPM accuracy at low speeds, it was difficulty to have a look on, because we were expecting it to be 0 when the motor was standing still, but we got values like 30 or 40, and we had to change those just to have useful values in Grafana. Another thing is that on Arduino, we only had the analog digital converters, so we had to make serial connection between the Raspberry Pi and the Arduino to get it working.
So also, you have maybe mentioned before, in Grafana, the values only refreshes every 5 seconds, and that makes it hard to have real-time applications or real-time dashboards. So that's one difficulty we found. But also the data modeling itself, especially at the beginning, was kind of challenging for us, because we didn't have a clue how we put up the trends and the types and all that planning. Also, a very big problem was that the Arduino, which is also controlling the motor script, the motor controlling script, is deterministic, obviously. And this Arduino is processing this motor script, but also needs to send the data to the Raspberry via I2C, and exactly at this time point where the Arduino is sending these data to the Raspberry, the motor script is blocked or paused, and then you get some mini pauses in the movement of the motor. It's kind of small because you didn't see it very good in the video, but it's worth to mention.
So for the end of our presentation, we want to give a look into the future, what we can do with this digital twin. Let's talk about predictive maintenance. Our machine condition normally operates at this state, but when there's a failure being initiated, the condition will be worse. So like our motor starts heating up, for example, and the inside of the motor is maybe being damaged. So this is where predictive maintenance is very important for us. We can measure the important values and make some changes, like having a cooling for the motor, or if the vibrations are getting out of hand, maybe there's something in the inside of the motor not working correctly. So predictive maintenance is important for us not to get to the point of failure here. Yeah, we can detect misbehaviors and damages. Thanks for your attention. This was our presentation for the digital twin for our stepper motor. Bye.
Thank you. Bye-bye.